Much as any other student that I've known, Eric has taken advantage of the educational process, both at MIT and at Stanford. He got a dual bachelor's in physics and electrical engineering at MIT, and a master's through their co-op program together with IBM, all in the 5-year period that he was there, ending in 1999, right? And that involved a number of things, including his co-founding of the Society of Physics Students at MIT, which I checked in your research, which I checked in the web, and is still a functioning organization and has all the typical geeky characteristics of any good MIT organization. And actually, they have a whole founding chart and everything, which I imagine you were involved in. And also, then that involved 2 or 3 summers at IBM. 3 summers at IBM, and subsequently, Eric has maintained his relationship with IBM through summer internships and also through his work with the SRC. So he joined Stanford working on the PhD in 1999, and he has worked with Professor Bob Dutton and myself jointly on kind of understanding the nanoscale physics of heat generation and transistors. And he's part of work by a couple students, also including Sanjeev Sinha, who's in the back somewhere, I think, who's involved on kind of the phonon side of this project. So in my group, sitting upstairs in building 500, these guys are the electron and phonon members of the research group. And I should say that Eric has, along with Sanjeev, but Eric also has gotten really excellent reviews for his work from the Semiconductor Research Corporation. They gave him a fellowship to pursue his studies. IBM co-sponsored it with SRC, and I think one year, 2001, we received the highest ratings in recent memory at the SRC review for the contract where both Sanjeev and Eric were reporting. So he's going to tell you about that today. I should say that Eric has also taken advantage of extracurricular activities. He's a DJ and a manager for former manager for KZSU, and his radio show Thursday 6 to 8 is Poptronica, which is a blend of various modern pop, jazz, electronic. And I actually checked out a few of your blended musical riffs and showed a lot of creativity. So, Eric.
Thank you, Ken. The radio show's off the air right now, actually. I have been focusing on just on this for a while. So the title of my talk today, in fact, there were, Sanjeev, do we still have handouts?
Yes, I think we have.
All right, so if you guys, there were some handouts with the slides, if you guys want to pick them up on your way out or in general. The title of the talk today is Self-Heating and Scaling of Silicon Nanotransistors, and that's what I'll be talking about. Now, I want to summarize to begin with. First of all, we're going to be talking about some of the physics of heat generation in bulk and in strained silicon, how the heat is generated. And I'm going to be introducing this Monte Carlo code, which I wrote from the ground up, called MONET, and we're going to be talking about how it's implemented. We're going to be talking how the electron and the phonon models are implemented in this particular case in some novel ways. We're going to be validating it compared to data and compared to some commercial codes in the limits where these are applicable, of course. We're going to be talking about the real results of this heat generation work, which are the heat generation details, both the spectrum of heat generation and also the location of heat generation in nanoscale silicon transistors. And then we're going to switch gears a little bit and actually get into device scaling. And we're going to be talking about the thermal scaling limits of nanotransistors, specifically thin body, fully depleted transistors. We've developed a compact model for such a device, a compact thermal model, which contains self-consistent electrothermal analysis as well. And I'm going to be talking about device geometry optimization and how one might be able to make these devices, to build these devices such that they are more impervious to the own heat that they generate. So kind of as an introduction, the way I'd like to think about heating in electronics starts with a light bulb. I think it's the simplest example. You run current through a light bulb, it heats up. In fact, more than 90% of the power that you put in a light bulb doesn't come out as light, it comes out as heat. So, and you know, the resistance of the filament for metals usually goes up approximately linearly with temperature. The resistance for doped silicon goes up more than linearly with temperature. And the other thing that I want to get at is that the power in, you know, in your regular light bulb at home is about 100 watts. And that's kind of an interesting number because the power in your CPU these days is also about 100 watts. In fact, it's about 100 watts per square centimeter. And what people have been able to do with 100 watts per square centimeter is cook an egg directly on top of an AMD CPU. Somebody actually did this. There's the URL if you're interested. He took off the heat sink, he put a little aluminum tray, put the egg sunny side up, and 10 minutes later, there it was. Apparently, it even tasted good. So clearly, there's a lot of heat coming out from these processors, and one of the things that we want to do with it is we want to try to get rid of it because it's damaging to performance and to the scaling of these processors. And one of the things that some brilliant engineers at this company called Asus Tech did is they came up with this very inconvenient heating solution. I don't see that making it into any computer anytime soon, at least not into a home desktop or especially not into a laptop. So that's pretty. I find that pretty inconvenient for cooling a chip. And speaking of laptops, the other danger with laptops is that they can burn you. And in fact, the industry doesn't call them laptops anymore. They refer to them as portables or notebooks. So be careful. Now, getting on to the more serious part of this heat generation problem is how can you manage the heat that's generated? So the heat, we're convinced that the heat is generated, it's there, current is running, things are heating up. Let's talk about how we can manage this heat. I would like to give you a top-down look at how this heat can be taken care of. And one of the ways to do it, at the system level, as I'd like to call it, is to replace the heat sink and the fan that's sitting on top of the CPU with something better. And Professor Goodson's company, Coolidge, is actually working on commercializing this right now. They're talking about, or they're doing, some microchannels, etched microchannels on the back of the CPU, and they're running water through them and then pumping the water out of there and dumping the heat somewhere else, which is where the fan and the heat sink is. Another way to do this might be to, and people are also doing this right now, especially in laptop processors, is to do it at the circuit and the software level. What people are doing is they're actively managing the power in different parts of the CPU. And people also know that if you write your algorithm in a certain way, the power dissipated in the CPU actually is a function of the algorithm that you're writing. So you can write software in ways in which less power is generated in the chip. And really what this talk is about is about managing this power at the transistor level. I put a question mark there because this is really what I'm proposing. Can you do something about the power at transistor level? Can you at least design a transistor so it self-heats a little bit less? It takes the heat at least outside of the active region of the device. And we're going to be talking about the electrothermal device design. So let's look at some trends in the industry. In the past 10 years, there's been some exponential trends. Some people refer to them as Moore's law. I don't really think it's a law, but it's, well, people can argue if it's a law or not. But it's a self-fulfilling prophecy, really. And it really shows tremendous, obviously, tremendous acceleration in advancement of these transistors and these chips. On the left, where I've got is transistor count in millions. On the right is where I have the power density per chip for AMD Intel PowerPC chips. And again, if you look at the vertical axis and you realize that it's logarithmic, you will see that these are exponential trends as a function of time. And actually, if you extend, right now we're looking at 100 million transistors per chip, and we're looking at, I was saying earlier, about 100 watts per square centimeter dissipated in these chips. And the thing that worries people like me is that if you extend these trends, especially the power trend, you actually end up in power densities which are unmanageable. Some people have actually argued that you would end up in power densities typical of or rocket nozzle, which obviously are not something you can live with in a chip. And from a transistor point of view, because I'm a device engineer, there's this march towards confined geometries and novel materials in transistor design, introducing germanium, introducing silicides, introducing thin silicon films, silicon dioxide, all of which are much worse thermal conductors than silicon. And what I've got on the right listed is the thermal conductivity of these different materials. And we're going to be talking a lot more about that, or about how that plays into the heating part of transistors. I want to look at the details of Joule heat generation of silicon. Joule heating is really just heating occurring from the current flow. And so when you set up an electric field in a transistor, the electrons are zipping from source to drain, as shown in the cartoon on the top right. It's actually a fake colored EM from IBM. And the electrons are gaining energy from the electric field, of course, this energy E. And what is happening with electrons with energies, the not so hot electrons, energies with electrons below about 50 milli-electron volts, they tend to scatter preferentially with the acoustic phonon modes in silicon. And the acoustic phonon modes in silicon are the fast ones. They are average velocity, sound velocity in silicon, which is about, depending on the branch, 5 to 9,000 meters per second. And so they carry the heat away to the package well. Now, if you talk about electrons with energies above 50 milli-electron volts, which are most of the electrons in a regular transistor, they tend to scatter preferentially with optical phonons. Optical phonons are the top branches in the phonon dispersion relationship on the right. And they have group velocities which are much slower than those of acoustic phonons. And so they just kind of sit there until they decay to the acoustic phonons, and then the acoustic phonons take the heat out of the package. If you're not familiar with the phonon dispersion relationship, I'm assuming most of you are familiar with the energy band diagram in silicon. The phonon dispersion relationship is essentially just due to the periodicity of the lattice, only certain frequencies of lattice vibrations are allowed. And that's the plot of the frequencies that are allowed as a function of the wave vector of these frequencies. And that's essentially what the phonons are. And the phonons in silicon and dielectric are the main carriers of heat, which is why we'll be talking a lot about the electron-phonon interaction and how the heat is generated. So, speaking of how the heat is generated, how do we compute the way the heat is generated? Well, I can think of at least 3 different ways in the context of an actual transistor simulation program. The simplest way would be to run a commercial code and essentially just extract, from drift diffusion point of view, extract the dot product between the current density and the electric field. And that's what I have plotted on the right. And I believe that's a fairly old plot. It's a 0.18 micron transistor. The problem with this approach, as pretty well known, is that the drift diffusion approach does not capture non-local transport. And what I mean by non-local transport is the fact that when you have very sharply peaked electric fields, the electrons actually tend to travel, or they will travel, several mean-free paths beyond this electric field before they release all their energy to the lattice. So what I'm trying to show on the cartoon on the right is that the electron will travel past the electric field peak, and the heat is deposited somewhere farther into the drain. And we'll see this in much detail in the latter part of the talk. Another way to do it is to turn a few more knobs in a commercial simulator like Medici, and to compute things in the hydrodynamic model. You compute the electron temperatures, and you also need some average scattering time that goes into that equation. And that's sort of one of the problems, is that you really need some average scattering time in there, and it's, as I will show later, the scattering rates or the average scattering times are actually pretty strongly energy dependent for electron and silicon. And also, both of these methods, both the drift diffusion and the hydrodynamic method, give us absolutely no information about the generated phonons. We don't know if the phonons are generated into the fast acoustic branches or the slow optical branches. And really, nobody has answered that question until now. So I decided to go ahead and, when I started this work, to look at the Monte Carlo method. Just because of this, because it actually has all the physics components in there. So really, the pros of the Monte Carlo method, if you want, is that it's great for non-local transport. It simulates each electron one at a time. So electrons obviously are allowed to travel, interact, and scatter as they should in the silicon lattice. And it gives us complete information about the generated phonon. So I can actually compute the heat generation rate essentially as the sum of the phonon generated minus the phonon absorbed, and divide by time and by volume, and that's my heat generation rate directly from the electron-phonon interaction. Of course, some of the cons of the Monte Carlo method is that it's slow, but there are some shortcuts that one can take. And I will talk about those for a bit as well, some of the shortcuts that I've taken. So how does one implement a Monte Carlo code specifically geared towards heat generation, which is what I've done? Well, first of all, one thing to keep in mind is, again, electrons simulated one by one. There's about 10,000 electrons in my grid in the device, sloshing around and obeying Newton's laws between collisions. And the method is called semi-classical because, like I was saying, the electrons obey Newton's law F equals ma with an m star in there, which is the effective mass, actually, accounting for interaction with the crystal. So electrons obey Newton's law essentially between scattering events, but the scattering probabilities and the state after scattering is actually computed quantum mechanically, starting with Fermi's golden rule, as we'll see. So that's why we call this a semi-classical method, because there's some classical physics in there, and there's some quantum physics in there as well. Of course, we need to run the simulation long enough to gather useful statistics. And the main ingredients of any Monte Carlo model are the electron energy band model, the phonon dispersion model, as we'll see. And when you talk about it in the context of an actual device, you also need to take into account purity scattering. Obviously, you need the Poisson equation to adjust the electric field self-consistently with the charge moving around. Any real device has boundaries. Those are quite difficult to implement in Monte Carlo simulations. And what I've done to actually deal with real devices is I've imported a grid from a commercial dispersion simulator from ADG, which I was talking about earlier as well. So I don't really have to deal with grid generation and such in my code. So now, like any self-respecting Monte Carlo code, I've given mine a name, and since he's one of my favorite artists, Monet, it also kind of sounds like Monte Carlo for electron transport if you kind of look at the letters. So if I refer to Monet from now on in the talk, you'll know that it's the same thing as my code. So let's see where the present work fits in historically with other existing Monte Carlo methods. Again, the two main ingredients are the electron band model, and there's varying degrees of sophistication for that. There's analytic bands, there's non-parabolic approximation, which is the correction, and then people have gone into full band mode for the past 20 years, actually. The only problem with full band codes is that they're very, very slow. You need to tabulate the entire energy band structure, and you need to look up where an electron is, compute its momentum, compute its energy, everything. Actually look it up. So it's a table lookup problem, so it's actually rather slow compared to an analytic description. The other dimension of this work is the phonon dispersion model. And as far as phonon dispersion models, including Monte Carlo, typically people have simply included longitudinal acoustic modes without any kind of dispersion, and they've assumed just fixed energies for the intervalley modes, for the optical modes, as we'll see. There's been some recent work which has taken into account both the longitudinal and transverse modes, but again assumed only fixed optical modes. And about 10 years ago, some very daring scientists have worked out a code that is obviously extremely slow, but it actually uses the full phonon dispersion from that's also computed just like the from ab initio, essentially, from basic principles, computed just like the electron band model. And the problem with these kinds of approaches is that they get very, very computationally expensive, especially for the full band and the full dispersion kind of approach. My code is somewhere in between. It fills a, as I was showing there, it fills basically the space between the full band codes. So it essentially treats the electron band model analytically, and it treats the phonon dispersion model analytically as well. So it keeps them to kind of an equal footing, equal sophistication. So let's look at the electron energy band model. That's basically the first ingredient for this code. On the left, I've got the full band model for the electron energies, the conduction band in silicon. And on the right, I've got the electron energy ellipsoids in momentum space, just for the bottoms of the conduction band values. So the bottom of the conduction band value is the part that is circled right there. It's also called the X value. The red part kind of goes through the X, but it's called the X value as well. It's near the X symmetry point in the Brillouin zone. And lucky for us, the energy bands near the bottom, the band structure near the bottom of the bands can be described analytically. And it can be described analytically in this non-parabolic approximation, which is what I've used in my work as such. And that's how those 6 equivalent energy ellipsoids are occur. And this is actually a good choice for nanoscale electronics simulations, in the sense that nanoscale electronics are expected to work at voltages on the order of 1 volt or below, which happens to be the band gap in silicon. So impact ionization is severely reduced in future technologies. Also, there's no X to L intervalley scattering. The L valley is up towards the left of the X valley, so it's more than 1 EV above it. So electrons typically are not going to scatter up into that valley in silicon. And again, like I was saying earlier, there's no table lookup involved. So it's relatively fast and reasonable. So this is the approximation that I went with. Now, another way to kind of make sure that I'm doing the right thing is to also plot the density of states in silicon. So I plot the density of states in the analytic band approximation and also the full band from a full band code. And you can see that even beyond 1.5 EV, they look pretty good. They're actually pretty close. And it's the density of states which really count as far as the scattering rates are concerned. So now let's look at phonon dispersion model. Again, I'm starting with the full phonon dispersion from neutron scattering data plotted in silicon along the 3 main crystal directions. What I've got here, again, is the frequency on the right. It's the equivalent energy in milli-electron volts for these phonons, and on the horizontal axis, the wave vector. And what I've done is I've looked at this, and I've said, you know, I can probably use, or I can use just the 100 part of this dispersion relationship and assume it to be isotropic all the way around. So that's what I've done, is I've looked at just the 100 direction of the phonon dispersion in silicon, and I've used this quadratic approximation. Again, a very simple quadratic approximation, very fast rather than the Monte Carlo code. But for the first time in an analytic band code, we are making the distinction between all the phonon dispersion branches. And that's what this really is doing. The optical phonons, the transverse, the acoustic, the longitudinal branches, all of them are taken about separately using this quadratic approximation. And these are included, as we will see, for computing all the scattering rates and also selecting the final state. And one of the other nice things about the way this problem is implemented is that it's fairly easy to extend this to other materials to any kind of change in the phonon dispersion due to strain or confinement as well, as long as you have another analytic approximation for the phonon dispersion in those materials. Typical Monte Carlo code, like I was showing a bit earlier, generally uses just one type of dispersion, just simple dispersion for the acoustic modes and a flat single energy for the optical modes. So that's what we're really improving on, especially since we're interested in which phonons exactly are generated, which is what we're working towards. Speaking of which, let's look at the electron-phonon scattering interaction in silicon. Again, we've got the 6 equivalent energy bands in silicon, which is where most of the transfer takes place. On the right, I have my approximation of the phonon dispersion. And as I was saying earlier, for electron energies below 50 milli-electron volts, they tend to scatter mainly inside one of these values. That's called intra-valley scattering. They tend to scatter with the acoustic phonon modes. And for electron energies above 50 MeV and some below, they tend to scatter between these valleys. And there are 2 types of inter-valley scattering events. There's a G-type scattering event and an F-type scattering event. And it so happens that, and this has been worked out from geometrical selection rules by some physicists in the 60s, actually. It so happens that the phonons that are generated, they can be computed, again, from geometrical selection rules, and it happens that they lie along the 1-0 direction. So this is another reason why using the phonon dispersion along the 1-0 direction is actually a good approximation as well. So the G-type phonon is 0.3 of the way to the edge of the Brillouin zone, and the F-type phonon is just 11 degrees off the 1-0 direction, but it's a phonon at the edge of the Brillouin zone. The scattering deformation potentials are also a very important ingredient for the electron-phonon scattering rates. And what I've got at the top there is the electron-phonon scattering rate is essentially written, like I was saying earlier, starting with Fermi's golden rule. And the main components of the electron-phonon scattering rate are the phonon occupation number, N sub q, with plus or minus for emission and absorption. And the G of E plus minus h bar omega is the density of states in the final state, which is why the density of states is very important in Monte Carlo. So obviously, the more states you have to scatter into, the more likely you are to scatter. So it makes sense that the density of states would enter the scattering rate calculation. And the d squared, or d sub e squared, which is in there and I pointed to with a red arrow, is this scattering deformation potential, which is essentially a constant which people have generally computed or extracted empirically from transport data. And there are values for it for intra-valley and for intra-valley scattering rates. And the approach in this work, which is a novel approach, is what I've shown, highlighted in yellow on the slide. Really, the intra-valley scattering rates were originally computed almost 50 years ago by Herring and Volk as a function of theta, the angle between the phonon vector and the longitudinal axis of the valley. However, the uniaxial shear and dilation potentials that go inside the Herring-Volk expression were actually not known with some degree of certainty up until 10 years ago, so up until 40 years later, through the work of Yoder, Fischetti, and Laux. So what I've done is I've taken those 2 results, I've averaged over the angle theta throughout the Brillouin zone to keep in tune with my isotropic phonon dispersion approximation. And I've come up with these average potentials for the scattering with transverse and longitudinal acoustic modes. Those are the 2 expressions there. Notice that the theta value is gone. And now I can actually compute these. And I've got certain values that go in my code. Now for inter-valley scattering, there are 3 F-type phonons and 3 G-type phonons. And remember, these are the ones given by geometrical selection rules. So they're pretty well known in terms of their energy. The only thing that's been under some debate over the past 20 years is the strength of each phonon scattering process. And the old model that most of the literature has been using over the past 20 years is Jacoboni's model. And as I will show you, Jacoboni's model, and people actually have known this for a while, Jacoboni's model is not good. Works in bulk silicon, but does not work in strength silicon. In fact, people who have been doing strength silicon simulations have actually had to change the model parameters. So people who are doing strength silicon are working with one set of parameters. People who are doing bulk silicon are working with one set of parameters. So the set of differential potentials which I was able to extract from the data that I had available actually works in both, which I will show you soon. And one of the nice things about these results that I extracted is that they're actually consistent with some recent ab initio calculations done by a group in Japan. And the agreement was serendipitous, and I say that because I had extracted these numbers empirically before I became aware of the theoretical work of these Japanese physicists. But the numbers actually work out to be about the same. So I'll show you why I'm saying these things work rather well across a huge range of electric fields and temperatures. What I've got plotted here is the drift velocity of electrons in silicon as a function of electric field. Very typical plot. We see saturation occurring at about 10 to the 7 centimeters per second. It's a function of temperature, of course. And on the right, I've got mobility, low field mobility as a function of temperature, spanning the temperature range from 45 to 600 Kelvin. So there's a big range of temperatures and electric fields that this code seems to, works quite well. This is in bulk silicon. This is described in detail, and how the extraction of these coefficients was done is described in detail in the Journal of Applied Physics paper that is coming out in a few months. And also, the other part that's explained in that paper is how the work using the strained silicon data was done. So now, the strained silicon data, the best strained silicon data on MOSFETs was not available up until 10 years ago, whereas the original Jacoboni model was extracted 20 years ago. So this data wasn't around when they did their work. That's the first thing I have to point out. If you're not familiar with strained silicon, I should point out that what happens when you grow a layer of silicon on top of the silicon germanium is that the larger lattice spacing of silicon germanium forces the silicon atoms to kind of stretch out and take on this larger lattice constant, at least in the horizontal direction. So it creates this biaxial tension, and the biaxial tension splits the 6 equivalent energy ellipsoids. It splits them between the four green ones and the 2 red ones. And then the strain introduces a splitting, which is proportional to the amount of germanium that you have in the substrate, to this fraction of X of germanium in the substrate. So now, if you have, let's say, a typical value for germanium substrate fraction is about 0.3. If you have 0.3 X in the substrate, this energy splitting is about 0.2 eV. Now remember that the strongest, the highest phonons available in silicon are about 50 to 60 MeV, so 0.05 eV. So 0.2 versus 0.05 eV. Which means that F-type phonon scattering is actually forbidden, at least at low fields. That's one of the main advantages of strained silicon. It actually eliminates one type of scattering event between the delta 2 and the delta 4 axes. So you're eliminating part of the electron phonon scattering. And on the other hand, it turns out that the effective mass of the lower delta 2 values, where most of the conduction takes place, at least at low fields, is the lighter transverse effective mass of silicon, which is 5 times lighter than the large Joule effective mass of silicon. So both of these actually lead to a mobility enhancement in strained silicon, which is fairly well known and understood effect. What is not so well understood is how to really model it, at least in MOSFETs. The reason I'm looking at MOSFETs is because MOSFETs, strained MOSFET mobility data, there's actually a lot more stuff going on in a MOSFET as opposed to a MOSFET. In a MOSFET, you have surface scattering, you have impurity scattering. In MOSFET, the most you have at room temperature is remote impurity scattering. So if you're really talking about the electron-phonon interaction, and you really don't want to have your simulation complicated by other models, such as impurity scattering or surface scattering, you really should be looking at MOSFET data, not at MOSFET data. And so what I'm plotting there is basically I'm plotting a simulation of the present work compared to a simulation with the old parameter set as compared to this data. The cleanest MOSFET data that's available in literature was done 10 years ago at IBM. So you see the mobility enhancement actually being modeled much better. And this basically indicates that there's a lot less F phonon, not a lot less, but there's somewhat less F phonon. I'm sorry, there's more F phonon scattering in silicon than people were originally thinking because only if there's more phonon type scattering, and then if you're removing some of it, we can get the extra mobility enhancement that we're seeing. Another way to quickly do a check is also from Ismail's data from '93, is to look at the drift velocity as a function of electric field, also available on strained silicon. The modeling there is also quite good, and also once we start talking about impurity scattering in devices, it's important to also check the impurity scattering in there. And this is just, I'm not going to talk about it, but I've taken an efficient impurity scattering model from the literature and I implemented it in my code. So it's really nothing new there. So really one of the main results of this work is this computed phonon generation, the spectrum of phonon generation in silicon. What I've got here on the left is I have the phonon dispersion ratio, which by now you should be pretty familiar with. On the right, what I have is I have the phonon generation rates in bulk and strained silicon, both at low fields, at relatively low field, the two middle ones, and the two on the right are at high field. Now there's a number of things that are perhaps interesting to notice here. First of all, besides the fact that we are getting complete spectral information on the phonon generation rates, knowing exactly how many optical and acoustic phonons are generated, what their wave vectors, what their energies are. Interesting thing to notice is that we can clearly see the effect of the scattering selection rules. We can also see the fact that there's less F scattering in strained silicon. So if you see at 50 MeV up there, the number of F-type phonons generated in strained silicon at low fields is significantly less than bulk silicon. On the other hand, at high fields, the phonon generation, the heat generation at high fields in bulk and strained silicon is essentially identical. The two plots on the right are, as far as I can tell, pretty much the same, even though they were done on very different systems. And that's because when you go to high fields, electrons are energetic enough that they actually have the energy to scatter between those two, the splitting in the energy bands there, where they would be forbidden at low fields. So this F-type phonon scattering event happens once again at high fields. So now you might ask yourself, what do we do with these wealth of information about heat generation in silicon, and what do we do? And this is a slide I borrowed from the thesis of my colleague Sanjeev Sinha. This is also described in a paper that we jointly sent to a conference, hopefully to the Journal of Applied Physics. And what he's done is he's written the code that solves the phonon-Boltzmann transport equation, starting with the phonon generation rates, which are provided from my work. So now we know, we're trying to figure out how these phonons actually evolve in silicon. And one of the things that we're learning is that the mean free paths of these emitted phonons are actually a lot less than the mean free path of thermal phonons in silicon. So they're actually much more localized near the region where they're produced, these phonons. They don't travel near as far. And also the other thing that we're learning is that the phonon relaxation rates, they actually depend on the peak generation rates in the device. And these peak generation rates is what I'm going to be talking about next in the context of the device and how they might be computed using this method and other methods. So let's first talk about one-dimensional devices. This NIN type device is kind of the Monte Carlo physicist's darling in the sense that it's just a simple resistor with a lightly doped or undoped region in the middle. But really the nice part about this is that it has the same band diagram, essentially the same band diagram, very, very similar to that in the channel of a MOSFET. So it's got the little bump, electrons are injected into the so-called channel and they drift into the drain. So we'll see how that happens. Qualitatively speaking with this movie. So again, you see electrons being injected across the energy barrier into the so-called channel, into the intrinsic region, and then drifting into the drain. And you'll see that pretty energetic electrons travel quite far into the drain. And now you have to remember that impurity scattering, everything is taken into account here. So electrons are scattering against impurities. They're releasing their energy to the lattice. And yet the energy is carried pretty far into the drain, as we'll see. So that was 1 picosecond in the life of an IN structure. So now let's see some results, some simulation results, where all the statistics are actually taken into account and we just run long enough. I've compared simulations done with my code and simulations done with Medici, the commercial simulator for this one-dimensional structure. And I've compared them for 3 lengths of this intrinsic region in the middle, 500 nanometers, 100, and 20 nanometers. And what one would expect is that the commercial code, the drift diffusion code, and Monte Carlo should actually give the same results in the limit of a long device, the limit of a 500 nanometer device. And indeed, what I'm showing at the top is the potentials are essentially identical. The blue line is the Monte Carlo potential, the red line is the Medici potential, computed self-consistently with the electric field at every time step. We're also seeing that the heat generation rates, which I'm plotting here on these new plots, new set of plots, the heat generation rates in the 500 nanometer device are quite similar. There's only about 10% error between the location and the peak of these heat generation rates, computed from J.E and computed from the sum of phonons, which I'm doing in this code. However, as we go to the 100 nanometer device, and especially to the 20 nanometer device, we see that the result in the heat generation rate is quite different in Monte Carlo compared to the diffusion code. And first of all, the first thing that we're seeing is that the peak is pushed into the drain. And the other thing that we're seeing is that the magnitude of the peak is actually quite different as well, because the electrons are actually traveling much farther to the drain. Again, this is part of the non-local transport I was talking about earlier.
What's the difference in Medici? Physics model of scattering?
This is J.E. This is just a J.E. model. It's a drift diffusion.
It doesn't use the same phonon dispersion.
Oh no, Medici doesn't use one. So the error, for a 100 nanometer device is about close to 40%. The error for a 20 nanometer device is 80%. So it's significantly more. Now, one of the things so first of all, we're highlighting the importance of the non-local transport in short devices. And the other thing that I'm showing here, and I'm only showing the integrated scattering rate, the integrated generation rates, but with purple and green, respectively, the optical and the acoustic generation rates are shown in there as well. So it obviously provides all this information about which phonons are generated inside the device. We can also run the simulation in the context of a two-dimensional thin-body transistor, although I have to say we can only run it qualitatively speaking, because the Poisson equation is not included in the simulation. It was never my intention to build a commercial simulator from ground up. Commercial simulators have been built, people have worked on them for 20 years. I'm after the new physics, some new physics here. But I can still look, if I put in the boundary scattering, and I import the electric fields from a commercial code like Medici, I can still look at how electrons, qualitatively speaking, are behaving in one of these 18 nanometer thin body devices. And if you look at this, you will actually see that the electrons are injected across the channel on average. There is net electron flow towards the right. And that electrons are warming up as they travel across the channel. That's the energy scale on the right. They're gaining energy, they're turning red. And that the red electrons are actually traveling quite far into the drain. Some of them are even exiting the contact while they're still pretty hot. Meaning that a lot of this heat is actually trying to drain, which qualitatively is what we were seeing in the one-dimensional device too. Except all the physics were included there, whereas this one is a little bit more qualitative. So a lot of this is, you can actually find out a lot more about this online. I set up this website. You can read a lot more about this code there. And the code is not available for download yet, but the movies are. These movies are up there. And also, the people who are running the Purdue Nano Hub have invited me to upload the code there, which is something that hasn't happened yet. And it won't happen until the code is properly documented. But I hope to do that as well. So now, what can we say about device design? We've learned about Monte Carlo analysis. We know some things about heat generation. We know a lot of things, actually, about heat generation in silicon now that we didn't know before when I started. And there's also this wealth of information about thermal conductivity and thermal properties of materials in the Goodson group that I was hoping to kind of put together and say something about design and scaling of nanoscale devices. So let's look at the evolution of transistor designs over the years. We are currently still in the regime of the bulk FET. The bulk FET is the workhorse of the semiconductor industry. It's essentially, it's used everywhere. People are starting to use SOI and strained silicon as well in commercial processors these days. So the strained silicon or germanium channel would offer a mobility improvement. That's another evolutionary change. And then also people are, of course, investigating FinFETs. That's a little bit more of a research topic. I don't think there are any commercial products using FinFETs yet, and there are no commercial products using germanium in a insulator device. In fact, that's a very, very recent research topic about getting very thin germanium films on insulator and taking advantage of mobility improvement in that. However, what's happening here is because of the confined geometries and because of the buried oxide that is usually that's stuck below these transistors have actually much poorer thermal properties than bulk silicon, and that's essentially what I'll be looking at for the rest of this talk. One could say that from a thermal perspective, the transistor evolution is actually not going too well. That's the point I'm trying to make. So let's look at this ultra-thin body transistor. That is an actual transistor built by Intel, who originally, many years ago, used to say that they would never go into SOI, but they did in 2001 at IBM. This is, they don't call it SOI.
They don't call it SOI.
They call it
fully depleted transistor.
fully depleted, yes. DST, that's right. It's the depleted substrate transistor. And on the right is essentially a thermal circuit model representation of this transistor, of how the heat might flow. Now that we know that heat is generated, how the heat might flow around this transistor. And the resistances can be computed fairly simply using, it's just a lumped resistance model. One of the important things to realize here for the scaling study is that the thickness of the silicon layer, and I've highlighted that in red, the thickness of the silicon layer is generally assumed to scale as the gate length divided by 4. This is for purely electrostatic reasons. This is how you get a full depleted substrate, and this is how you get good short channel characteristics. And for a FinFET, the thickness of the silicon fin is actually can be relaxed the requirement, so it can actually be a little bit thicker, which we'll see is actually better for heat transfer. So if I take this model, I can actually look at it from above and then assume that the FinFET gate is actually over the channel, and I can still apply. Then I'm taking the on current, the voltage, the oxide thickness, and so on, and then the threshold voltages from the ITRS technology roadmap guidelines. So one of the first things that's happening when you go to thin films is that the thermal conductivity of the thin film is significantly reduced from bulk. The bulk thermal conductivity in silicon is 148 watts per meter Kelvin. In thin films, it's reduced a lot. Experimentally speaking, the thinnest film that's been measured by Professor Ashiki's group at Carnegie Mellon are 20 nanometer thin films, and they've measured about 22 watts per meter Kelvin thermal conductivity. We can also use a simple theoretical model like the one I've implemented here to extend this and to look at thermal conductivities of thinner films, such as 10 nanometers, 5 nanometers, and so on. So for example, for a 10 nanometer thin film, thermal conductivity of silicon is reduced from bulk by more than a factor of 10, which is bad news for thermal behavior. And why is this happening? This is happening because we have strong phonon boundary and phonon impurity scattering in these thin films. So this is leading to a strong reduction of thermal conductivity. Again, we're assuming in this plot, I'm actually plotting the thermal conductivity as a function of technology node, and I'm assuming that the thickness of the silicon layer goes as 1/4 the gate length for depleted devices. And I'm also showing you what it might mean to make that layer a little bit thicker from a factor of 1 to 5. So obviously you get some increase in thermal conductivity that way. The other thing that I'd like to look at is when you put a metal gate on top of an oxide, on top of a thin oxide, the measured thermal resistance of that thin oxide is actually stronger or larger than you would expect by simply using this thermal conductivity formula, the thickness of the oxide divided by the oxide thermal conductivity divided by the area. And what people, several research groups have found, and the data is compiled on this one plot, is that there's an extra component to the thermal resistance of these structures, these metal oxide semiconductor structures. And this is fairly constant. People have all research groups have converged on this one value, and it seems to be that the thermal bond resistance value for this kind of a material sandwich is on the order of being equivalent to a 20 nanometer oxide. So this means that if you create a 2 nanometer oxide and you have a metal gate on top of it, the thermal resistance of the structure is still going to be equivalent to about 20 nanometers of oxide. So you can't really win by making a thinner oxide thermally. Electrically, you still win, but thermally, you don't really win. There's still some debate in the literature about where this boundary thermal resistance comes from. It can come from phonon dispersion mismatch between materials. It can come from the fact that the phonons are the heat conductors in dielectrics. The electrons are the heat conductors in the metal, so there's heat conversion at the boundary. And it can also come from small metal grains or atomic roughness at the boundary. So perhaps improving processing condition might improve this, although this is the number that I've used in my simulation. This is the number that several research groups have found. Another contact resistance, boundary resistance, if you will, is that at the contacts, at the actual, we're talking about the actual contacts to the source and the drain. Again, you have two dissimilar materials. You have metal on top of silicide on top of silicon, doped silicon. And here there's a lot less data available. So what I've done is I've gotten in touch with some contacts in the industry, with our friends at Texas Instruments. We've obtained some wafers from this group, and we've done some Kelvin probe measurements. And these are very, very simple measurements. In fact, they're very simple electrical resistance thermometry measurements, which work something like this. you can measure the electrical resistance of these Kelvin probes as a function of temperature, as a function of different shut temperatures. So you can get a formula for the electrical resistance of the contact as a function of temperature. Then you can also pump more current to these contacts. So you can measure the electrical resistance as a function of power, which is what I'm plotting over there. Then you can correlate this power with the temperature that you were doing these measurements with. So you have a relationship between temperature and power. If you have a relationship between temperature and power, you have the thermal resistance of the contact. And that's what I'm extracting here. Thermal resistance, and this is a lumped thermal resistance between the contact and the thermal ground. But this is the thermal resistance that I'm using in this model. And there are several components in this, and we can talk a lot about what these other components are. It's very, very difficult to separate them, to separate between them. But it turns out that I can take this resistance and I can stick it right between the source and the thermal ground in my model. And I don't, at this stage, I don't have to worry about the separate components of the thermal resistance. So speaking of the model, let's look at it. I've rewritten the resistive network before as the circuit on the left. I'm also showing you the parasitic capacitors that are available, that are present in one of these transistors. And changing the geometry of the transistor around essentially affects two things. It will affect the thermal resistances involved in the device, of course, which in turn affect the temperatures of the device, which affect the current. The current affects the power, and the power again affects the temperature. So I have this self-consistent. This is a self-consistent part of the model. The temperature and the current are computed self-consistently. There's a simple model in here for what the current should look like as a function of temperature. The current is dependent on temperature through two parameters, the mobility and the threshold voltage. So those two are in there. And these are fairly well documented experimentally as well as theoretically values. So that's what I have in there. And also the geometry affects the capacitance of these fringing capacitors that are there. There's simple models for that as well. And these capacitance, combined with the current, the values of the current actually affects the intrinsic gate delay, which one computes for these capacitors. So essentially the speed of the capacitor. So let's look at the DC temperature, the source temperature rise along the ITRS guide, right down the ITRS roadmap, the technology roadmap, all the way down to the shortest SOI devices, using the power inputs from the roadmap, using all the dimensions from the roadmap. In fact, as recently as this year, Jenkins has reported temperature rises of DC of 100 degrees Celsius in very mundane 100 nanometer SOI devices. Basically what I'm plotting there as a parameter is the source and drain thickness of these devices. So what I'm showing you is that if I increase the source or the drain thickness, I actually have a lot more volume to dissipate heat into, especially considering the heat is generated inside the drain. And that actually leads to significantly decreased device temperatures. So people have talked about raising the source and the drain from an electrical standpoint because you reduce the electrical series resistance of these devices. As it turns out, the series thermal resistance also significantly reduced. So this leads to lower temperatures. So this is kind of a good design thing to keep in mind. Of course, as we'll see, you can't raise the source and the drain too much because you start running into parasitic capacitance problems. Let's do a quick comparison with FinFET, since FinFET can also be modeled with this interpretation. Again, remember the main difference, everything else being equal, the main difference between SO and FinFET is that the thickness of the fin is about twice bigger for FinFET. Because you have this gate going on top of it, so the electrostatics are relaxed because you have more electrostatic control of the gate. This is a good thing.
The previous slide was source temperature.
Yes, this is drain. Yeah. I just wanted to show one of each. Drain is a little bit higher, obviously, because that's where heat is generated. This is, yeah, I mean, it's the same simulation, but it's source and drain. What I'm seeing is that, well, on one hand, there is a limited fin height available, so there's going to be more phonon scattering with this fin height, which actually will end up leading to some reduction in thermal conductivity of the material. However, the fact that you have a twice thicker body and a twice thicker oxide area both lead to an increase in thermal conductivity and also a decrease in the oxide thermal resistance. And overall, as it turns out, when we put everything in at the same time, it turns out the FinFETs actually, for the same current power, same kind of assumptions, they should have lower temperatures than SOI devices. Let's do a quick comparison also with germanium insular devices. Again, we're comparing SOI and germanium insular devices. And These are results from a paper which was just accepted, I found out today, at IBM for this year. This is work that I co-authored with our in-house germanium expert, Shinan Chui. And the important thing, I guess, about germanium is that the thermal conductivity of germanium is worse than silicon. Usually people have talked about, germanium bulk devices as having some thermal problems because the thermal conductivity of bulk germanium is 40% that of bulk silicon. Now, when you go to thin films, it turns out they're both bad. They're both about equally. They're not quite equally bad. Germanium is still worse, but it's actually a little bit better than when you compare them in bulk. And if you take into account the fact that germanium has, well, in this simulation, I'm making the assumption germanium has a 2x mobility advantage, which is what's available right now in terms of the data that's available out there. And the fact that you can get about the same current drive for 40% lower VDD. Again, this is based on experimental data that whatever germanium devices are available right now. You can actually get the same current with lower power in the germanium device. So it's a little bit worse thermally, but you also get less power out of it. So when you put these two things together, it actually turns out that the temperature rise that I'm computing for these devices, again, these are computed self-consistently, are about the same. Germanium insulator and silicon insulator devices have about the same temperature rise when you put everything together. So the temperatures being about the same, germanium actually retains mobility and current advantage, at least in the germanium uninsulator form compared to SOI form. Let's look at what else we can do with the source and the drain. Electrically speaking, people have also generally tried to keep this extension, LEX, shorter. So you actually have, obviously you have a better, or lower rather, electrical series resistance. So besides raising the source and the drain, I'm also talking about making it wider and bringing it closer to the gate. What's happening, on the other hand, is that it's increasing the parasitic capacitances, and therefore probably killing my intrinsic gate delay. So this is what I'm looking at right now. Of course, thermally speaking, and electrically speaking, at least well, from the point of view of electrical resistance and thermal resistance, what we want is a short extension length and a tall raised source strip. On the other hand, there are other technological considerations here, but really what I'm going to look at is this gate-to-drain capacitance and what its impact might be on circuit performance. So let's look at intrinsic gate delay, which is simply just the CV over I product. C is the capacitance computed with some simple analytical formulas on the capacitors I was showing you earlier. Voltage is given by the ITRS guidelines, and the current is computed self-consistently using the simple electrothermal model, which I was proposing earlier. So we are seeing, I'm plotting the intrinsic delay as a function of technology node for SOI and germanium insulator devices. Remember, germanium insulator actually keeps mobility advantage, and it actually shows to have lower delay as well, as one would expect. But the interesting thing on the first plot is that as I raise the source and the drain, if I raise it beyond 3 times, about 3 times the thickness of the channel, I actually don't gain any more speed advantage because the parasitic capacitance starts to kill me. So the delay actually doesn't get any lower for about 3 to 4 times raised source drain. And also what I'm seeing is that the approximately optimal extension length is about 1/2 physical gate length for these devices with this simple model. So what I have on the right is I have this contour plots. These are optimization contour plots of intrinsic gate delay in picoseconds for an SOI and a GOI device, both with 18 nanometer gate length, and they're plotted as a function of source drain thickness and extension length, and you can see what the kind of the optimum design space is for the optimum electrothermal delay for these devices. And of course, we're seeing that the optimized germanium insulator devices maintain their speed advantage over SOI when all thermal considerations are taken into account. Finally, I'd like to just make kind of 2 more observations about the role of contact resistance and the role of power that we're putting into these devices. Again, I'm plotting the source temperature rise and DC as a function of gate length along the ITRS guidelines. And what I've done here is between the red and the blue line, I've reduced the contact thermal resistance. This is the thermal resistance between the via, the silicide, and the silicon. So I've reduced that, and in a way, what one could do with these contacts is the contacts could actually be used to spread heat. Just as one could increase the source and the drain to give more volume for heat to spread into. The same thing could be done with the contacts. At least that's what this model seems to indicate. Of course, more work has to be done to understand the contacts better thermally. There's very little understanding. This work is some of the first to kind of go in that direction, but a lot more work needs to be done to understand these contexts, thermally speaking, as well as more electrically, there's a lot more. And then the other thing that we could do, of course, we get more power. The ITRS guidelines right now are not very generous, actually are too generous with the power. What I've done is I said, well, remember, device areas and volumes are shrinking quadratically and cubically, respectively, with device channel length. So why don't I scale my power? I cannot put a constant amount of power in an infinitely shrinking device volume because I'm going to get infinite temperatures, obviously. So why don't I scale my power down quadratically as well? Let's strike it quadratically. So I use that simple formula, and it turns out that I can scale the power. If I scale the power quadratically, I can keep the temperature essentially constant. So I could call this isothermal device scale, for example. Those are kind of so. Besides lowering the power, which of course may not be possible from operational. I mean, people have different requirements for what they want the device to operate at, and so on. The other thing that could be done, of course, for the smallest SOI devices is to use them sparingly or to operate at a very low duty factor, because the smallest devices, when you turn them on and run the ITRS specified currents through them, you can't keep them at DC. They simply don't want to stay there, so they need to be operated at a low duty factor. So I have to summarize. We've started talking about self-heating ball-constrained silicon, and really about the physics of heat generation from current flow in silicon. I've talked about this code, MONET, how it's been implemented from the ground up. I've talked about how the electron and phonon model were implemented, how I validated against data and commercial codes where, of course, where appropriate, in the limiting cases where it's possible. And I've really shown some of the first work on the heat generation spectrum in silicon and in strained silicon, and also much improved understanding of where the heat is generated in a silicon device. Then we've switched gears a bit, and we talked about scaling limits from a thermal point of view of these nanotransistors. I introduced a fairly simplistic but very quick and kind of good for design compact model, and I believe a lot of physics has gone into this model. And we talked about this electrothermal geometry optimization of the device, and among other things, I also pointed out that it seems like FinFET and germanium insulator maintain some advantage, as people would expect. People have been expecting electrically over silicon uninsulated devices. There's some of the contributions from this work to the literature, the recently accepted IDM paper, Journal of Applied Physics paper. In fact, there were 3 IDM papers in the last 4 years that have come out of this work. The SRC, as Professor Goodson pointed out, has been quite fond of the work. They gave me a few best paper kind of awards when I went to their conferences. And I want to thank a lot of people. I want to thank my main advisors, Professor Ken Goodson and Bob Dutton, for advice. And for agreeing to supervise this project that kind of spans device physics and thermal sciences. I want to thank Professor Krishna Saraswat, KVHO, for being here today and asking tough questions later. And I want to thank Professor Jim Harris for essentially bringing me to Stanford, convincing me that Stanford was a great place to do a PhD at. Also need to thank Professor Atelias Delamo and Sid at MIT, who also convinced me that Stanford was a great place to go. I have to say they were right. Professor Lundstrom at Purdue, Ravioli at University of Illinois, Urbana-Champaign for a lot of interaction, answering a lot of my questions over email and conferences. My collaborators, graduate students that I've learned a lot from. Sanjeev, I've learned a lot of phonon physics and thermal stuff from. Xian, of course, I've learned a lot of germanium issues from. And Reza, I've learned some stuff about noise in devices from. I want to thank the people who really run our research groups, CC and Feli. I want to thank all the members of the 2 research groups. In industry, there's a number of people that I've interacted with. I spent 1 summer in graduate school at IBM as well, interacting with Pisketti Locks and Phil Oldridge's, particularly at Fishkill and Yorktown at IBM. Also keeping in touch with a number of people at AMD, Texas Instruments, Charbaka Devori, especially for providing the wafers. Jim Hutchman from the SRC has been a big fan of this work, great supporter, great person to know and run into. The Semiconductor Research Corporation has been paying for the last 4 years of my education, so big thanks to them. I'm not going to read them my list of friends, but they really kept me on occupied otherwise. I want to thank my family at the radio station and my real family, mom, dad, and my sister, Leah, who's here today. Someone there. Hi. Filming. Thanks.
Take a few questions in the open session.
In that last slide, you mentioned how you could use the duty factor maybe as a way of ameliorating this problem. That would seem to depend a little on having the appropriate time constant for your heating.
That's right.
Would you like to say something about that, please?
Yes. The time constant of these devices is on the order of nanoseconds. As far as we know, it's on the order of, for both devices, maybe about 15 nanoseconds. For SOI devices, it's more. Time constants are going to be shorter in the future, but the switching times of these devices are going to be much, much faster than nanoseconds. So, as long as the switching times are faster than the time constant of these devices, I think we can simply just, we can take the peak steady-state temperature that we compute with this model, and we can multiply that by the duty factor and actually get the average temperature that this device would experience. So the way I would extend this to to incorporate a duty factor, we can just simply multiply the peak steady-state temperature with the duty factor.
So your on time better be a lot shorter than your thermal time constant.
Absolutely. That's yes. Absolutely. That's another way to put it. Yeah.
Okay.
Other questions? Sure.
What's the value of the strain?
What is the value of the
Like
strain?
around what values of the strain?
I don't know the actual value of the strain, like the actual delta x over x. I know it in terms of, people usually talk about strain in terms of, at least in this field, they talk about strain in terms of the energy splitting that's introduced, and in terms of germanium substrate fraction you can introduce. I believe it's on the order of only a few percent. If you go beyond a few percent, you end up with with dislocations, with, I don't know the exact number, but it's just a very little bit. I think it goes from about, this lattice constant goes from about 5.43 angstroms to about 5.6, no more than that. You know, dislocation otherwise. Any question?
So I saw the model takes into account the heating due to the source drain current, but I didn't really see any factors for leakage from gates. Is that a big deal in the model?
Are you talking about gate leakage current or substrate leakage current?
Gate leakage.
Gate leakage current. There is that is not part of the model. I am assuming the oxide to be well behaved, so there is no